Hi everyone, in this video I will be sharing some of the exciting new features as part of the DSG 10ep.5.4 release. These new features are focused on enhancing the operational geology and geosteering workflow in DSG software. This video is split into 4 parts. The first part of the video will focus on the new feature of DSG 10ep.5.0 for Operations Geology. For those of you upgrading from the DSG 10ep.4 series, this first part of the video might be an interest to you. For those that are already in the DSG 10ep.5 series, the new feature of DSG 10ep.5.2 will be highlighted in the second part of the video. The third part of the video will focus on the features we added as part of DSG 10ep.5.3. The last part of the video is focusing on the latest feature we developed as part of DSG 10ep.5.4. For those interested in skipping ahead in the video, the timestamps are posted here. As part of DSG 10ep.5.0, we include the ability to lock and unlock preferred interpretations in the horizontal well correlation workflow. Via Interpretation Loader, you can now select interpretations that you wish to lock so that other users cannot edit them. This enhances the multi-user's HWC workflow by enabling the user to lock these interpretations, stopping unwanted edits, and ensuring the mapping workflow is kept evergreen with preferred interpretation. By locking down these interpretations, now you have gold standard interpretations that remain untainted by other interpreters' edits. Now let's take a look at new features for DSG 10ep.5.2. In this release, we will focus on the 2 new areas that center around the operational geology workflow. Both features operate on the horizontal well correlation license and will be available by upgrade request for those who have existing licenses. First, we have a new dedicated 3D view for well execution called Wellbore view, and the second new functionality is added to the classic horizontal well correlation workflow in the form of a new layers module. Let's dig into more detail for the first feature, the Wellbore view. The Wellbore view is a new view editor in DSG that centers around the drill bit as the well is being executed. The idea here is to provide a dedicated workspace for geoscientists who are operating their wells in real time. Using this new 3D view combined with other view editors like horizontal well correlation workspace, we can now get a focused look at the drill bit and the surrounding information that can impact drilling decisions. The Wellbore view feature displays a fixed position around the wellbore's bottom hole location that dynamically follow the TD as it is updated, giving users a third-person view of the well. Additionally, visualization enhancements have been added to this view editor, such as the display of notes in 3D, MD labeling, and data filtering around the wellbore. Tools such as a dynamic distance measuring tool, heads-up display, and features related to displaying data based on the TD update time have also been added. The purpose behind the Wellbore view editor is to provide a more accurate digital twin of wells as they are executed and to provide a simple 3D view with limited setups that operations teams can use to co-visualize relevant data and place the executing well in geologic contexts. Let's take a look at some of the visualization enhancements that have been made in this view. First, we have a series of fixed viewpoints available in this view in the top left-hand corner of the toolbar. We have a top-down view, a bottom-up view, and a left and right view. These views control the angle of the camera relative to the TD positioning. So, for example, the default is the top-down view here. We're looking down on this view at a 20 degrees angle at a distance that can be dynamically updated. You can use the scroll wheel in and out, or we have a bar here that updates dynamic zoom. What is great about these fixed views is that as the TD updates and more information is added to the well, the camera will center on that TD node and will refixate on that TD node at the same angle we have set for the fixed view. This leads to increased clarity on the different angles we can have in the scene and helps display your data in context to the surrounding information. Let's now have a look at some of the changes we made to viewing notes in 3 dimensions. There are 2 types of notes in DSG. The first one is called interpretation notes, which float in X, Y, Z space. The other, which is called well notes, which as the name implies, are tied to an individual well at a given measured depth. iNotes are now viewable in the new Wellbore viewer and in Cube View, with well notes being exclusive to the Wellbore viewer. We can now display these well notes in 3D and individualize how they are displayed on an individual level. Previously, we had the well note types be the overriding parameter for how we were going to display the well notes. Now we can individualize each well note as a separate entity, orient them with a right or left orientation, and control show or hide individual notes within these note types. We've also introduced some smart logic in 3D to prevent overposting of these notes, so the notes will dynamically change which side of the well they are displayed on for clarity of the display. We can use these well notes to show things that might be a risk when it comes to executing a well, things like microfractures that we may not have picked up on the seismic, or even formation evaluations that indicate where good formations may lie. All this ties back to displaying your risks and understanding those risks in a pre-drill scenario while you are executing your well. Now let's have a look at the visibility filter available in the Wellbore view. The idea behind this is to filter your data around your currently executing well, based on relevant information as deemed by the user. So, we have two different parameters we can set for the filter lateral extent here, which are the width and the height of the filter. We can filter several different data types including 3D grids, 2D grids, frameworks, horizons, and faults. Each data type operates independently from each other. This means you can filter out only 3D grids and leave normal display for 2D grids, and this does not impact other advanced visualization displays, things like overlay of the seismic attributes. Using this tool, you can increase the clarity of your data that's around your executing well by filtering out data that you've deemed unnecessary or irrelevant. Now let's turn our focus to some of the tools that I've built in the Wellbore viewer. Firstly, we have a dynamic measuring tool that measures the distance from the TD of the well to any object in the surrounding scene. We can make this static in that we can click on an object which will post the distance to that object related to the TD. As the TD updates, this distance will also update, meaning you can always keep track of hazards and surrounding information relative to your drill bit location. Next, let's look at the heads-up display. The heads-up display allows you to display a simple pop-up of information that is useful to communicate between geoscientists and drilling engineers. The idea here is to have a simple pop-up that reads out information such as total measure depth, vertical depth, survey depth from the directional survey, as well as inclination and azimuth, and some engineering parameters such as ROP. As with most things in the Wellbore view, this is designed to be updated on the fly as you add more information. This means you can always have the latest information at your fingertips to help with that communication between drilling engineers and well execution teams. Lastly, let's have a look at some of the features related to the TD information and how we can use that as a criteria filter on some of the information we're displaying in the Wellbore view. There are three main features added related to TD information displayed in Wellbore view. One is to color nodes based on activity. This allows you to color the bottom hole symbol based on some cutoffs in terms of TD update time. This stoplight system means you can always know which of your wells have been updated within a certain time constraint. For example, the wells shown in green here in the image have been updated within the last half hour. This means you can get a holistic approach to what your field view level is in terms of activity. This could be applied to much longer timescales. For example, if you wanted to see the wells drilled last year, you could set the time here to be relevant to that time frame. This means you don't have to keep going back and checking the database to figure out when the last update time for your well has been. This means you can get to work faster on analyzing the new information that has come in. Additionally, we've added a TD status bar, meaning if you hover over one of these bottom hole symbols, you can get a callout for the last time the TD was updated. Finally, we've added this feature to give a heartbeat function to wells as they're updated. Sometimes it may be difficult to see when a well is updated, particularly at a far back zoom scale. This allows you to see when the TD is updated by giving a blinking indicator, indicating the TD has been updated and is up to date. Now let's take a look at all these features combined with the Wellbore view to show them in action. Here you can see some information that I'm wanting to view in a Wellbore view. I have an actual well, which is an executing well showing green, and a well plan that I'm trying to execute upon shown in navy. You can see here I have the fixed view for the Wellbore viewer set to top down, and I can dynamically zoom in and out to set my zoom level. You'll notice as I update, the zoom remained fixed. When I update the well, you'll notice that the TD node, or the bottom hole symbol, changes colors to green, and you'll notice the blinking indicating the logs and updated. Here you can see various fixed views top down, left, right, and bottom up. These views will remain static, at least the angle will, as the well is updated. Here, I'm modifying the visibility filter, meaning you can filter out and things like 3D grids and framework surfaces in this case. You'll notice that I can also rotate within the scene. It does not have to be fixed, and I'm able to filter at a sublevel, my 3D grid, either based on layer or aerial extent on top of filtering it around my wellbore. The heads-up display is now being shown here, and you can see as I update the well, the information will also update on the fly. We can also see the measure distance tool in action here. When I activate that, it snaps to the TD node of my active well and gives me a straight line readout distance to any other data object. Notice that as I update the well, the information will also update, meaning I can use this in congruence with the HUD to provide accurate and updated information to my drilling team. You'll notice some of the TD tools I described earlier on display here. When I hover over the bottom hole symbol on a given well, you can see the TD update time. Additionally, here you can see the color by status shown in a stoplight style, meaning I can get a holistic view of my field and understand which of my wells have been updated within a given time frame. We can go to the bottom hole symbol dialog here to change the cutoffs for how we are displaying these different symbols. The final feature I'm showing here is the various well notes that we can display in the wellbore view. You can see that these are updated as I rotate around the scene so that they're not overposting, and they can be displayed in various ways on an individual basis in this well note details dialog box. We can use the wellbore view in combination with other well executing views such as a horizontal well correlation workspace to give a 3D view that doesn't need to be modified much to see what is going on. Here, you can see I'm updating my horizontal well correlation look ahead, and in real time I can see my well update in 3 dimensions and get read-offs from my HUD. All of this provides a collaborative workspace and a dedicated workspace for operations geologists to perform their work, giving new insights via a 3D view that provides a better representation of the digital twin. Finally, let's take a look at some changes made to HWC in DSG 10ep.5.4. Primarily, we added a new tab within the horizontal well correlation workspace called the Layers tab. This functions on a different algorithm to the traditional surfaces mode, which was limited to just a top-down geometric spacing. The new Layers tab means that you can set up your conformance amongst the different intervals in a similar way you can with the complex geology frameworks. You can have multiple layers in here represented by a top-down, proportional space, or bottom-up conformance, meaning the calculation we're using to calculate a predicted log can vary amongst the different layers. This is powerful in that you can use things like top-up conformance in areas that have a truncating unconformity to get a predicted log, whereas previously you were not able to do so. Additionally, we've added the ability to edit the surfaces themselves via control points on the surface, which updates the predictive log generated. This mode is perfect for generating a workspace, a sandbox-type workspace in which you can adjust the layers based on regional settings that you've deemed appropriate and see the impacts on a predicted log. The structure can be updated either for an individual surface or the whole framework. Control points can be added to choose a static point that will not change as you update the surfaces. Additionally, faults can be added, and throws can be adjusted to update your section. These new enhancements mean that you can do your pre-drill prognosis in a complex geologic setting and adjust the predicted log accordingly, allowing for more accurate representation and better analysis. Let's take a look at these features in more depth. In this field, you can see a complex geology setting with an unconformity coming through and truncating certain surfaces and some faults affecting the structure of the region. Using an offset well, you can now generate a synthetic log using complex geology rules and scenarios, allowing you to understand your reservoir and tweak your regional structure before drilling begins. The new editing mode, under the Horizontal Well Correlation Layers tab, enhances the understanding of the subsurface by utilizing dynamic framework to fill to construct a predicted log that accurately represents the structural model. In addition, this tool provides unique geologic layering rules that can be easily utilized to construct the predicting log curve that represents the subsurface current understanding. Here we can add surface control points and flex the surfaces to impact how the predicted log is calculated. We already established our layering information. We can add more things such as faults or dip adjustments to the actual surfaces themselves. Using this adjustment, we can generate a new predicted log and determine subseismic information such as faults that are not picked up from the seismic section or regional adjustment to the dip. Once the pre-drill evaluation has been completed, horizontal well correlation helps you understand real-time stratigraphic positioning through the correlation of the synthetic log and real-time log. Let's move on to the latest features I added for DSG 10ep.5.4. In this release, we will focus on the two new areas that center around the operational geology workflow. The first feature is an additional functionality for Wellbore view. This feature operates on the horizontal well correlation license and will be available by upgrade request for those who have existing licenses. The second new feature is a new feature called synthetic image log. This feature creates pre-drill structural analysis along the borehole. This feature will operate on the DSG Geology interpretation license. Let's start with the first feature. Wellbore View Alert Notification is an automatic notification system that will be triggered if the total depth of the well you currently monitored is within a certain proximity range of well notes. When the TD of the wellbore exceeds the proximity radius set, the alert notification will be triggered, and you will see a pop-up dialog showing the distance of your drill bit to the well notes, and descriptions of the well notes. Having the well notes interpreted around the wellbore and an automatic alert system will help Operations Geology to track the position of the bit. Using this feature, operation geologists and drilling engineers will be informed of subsurface conditions ahead of the drill bit. With detailed instructions and descriptions of well notes, it can improve the communication between operation and subsurface analysis to overcome the operation hazards. Here in DSG session, I have a well plan in red and my actual drilling well in green. I also posted interpreted well notes along my well plan trajectory. When the position of my actual well is updated, and it is crossing the alert radius set from well notes, then the alert notification system will be triggered. It will display a pop-up dialog called Well Note Alert. The Well Note Alert dialog will show the information on the distance between your actual well TD to the position of the well notes. It also shows the description of the well notes. On the Well Alert Notification dialog, you can see the Alert Summary option at the bottom of the dialog. Alert Summary contains the information of all the well notes that have been tagged as alert. Another option is called Well Note Details. In this dialog, you can pick and choose which well notes will be tagged as alerts to trigger the automatic alert notification. Moving on to the second feature. In the DSG 10ep.5.4 series, you can create synthetic sinusoids from the intersection between the well and the framework. From these intersections, the algorithm will compute structural components to draw sinusoid lines such as apparent dip angle, true dip angle, and true dip direction. The result of this intersection is plotted as a sinusoid line on a normal well correlation view or in an HWC horizontal correlation view. What is great about this feature is that it allows you to analyze the structure before well execution, and because this feature uses a framework as a reference, then the synthetic sinusoids will dynamically update if the reference framework is updated. This will give you advantages during operation to understand the position of the drill bit relative to the structure. Also, during operation, these synthetic sinusoids can be compared with image logs from MWDLWD and will improve your analysis and support faster geosteering decisions. If during operation you notice that the observation of the formation top is deeper or shallower, you can always incorporate this new formation top observation into the framework and the synthetic sinusoids will be updated during drilling. Let's see the workflow to create synthetic sinusoids. In the DSG session, I already prepared a framework that contains multiple surfaces. The blue well you are seeing on the screen is my well plan that I saved as an OpenWorks well, and I include this well on the framework building. From the well cross-section, I can see that my well plan is intersecting with multiple framework surfaces. Using the predicted tops feature, in well correlation I can display these intersections as predicted tops. Let's now focus on the well correlation view. Predicted tops from the framework intersections, as here displayed by the dashed lines, are representing the intersection points between the wellbore and the framework. In the background, the algorithm will extract and compute the structural properties such as true dip, apparent dip, and dip direction, and then draw a sinusoid line, we called it synthetic sinusoid, from those values. The computed synthetic sinusoids will be automatically displayed at the log track where you clicked it. And you can also notice there is synthetic sinusoid header appearing on the log track header. Because of the vertical scaling, the synthetic sinusoid lines might appear as flat lines, so you might need to zoom in to see the curvature or shape of the sinusoids. When you hover your mouse pointer at a sinusoid line, the cursor tooltips will give you information about the reference framework used, the framework surface intersected, true dip, apparent dip, and dip direction. Additionally, we added the feature of the properties of the borehole and sinusoids drawing reference. Using the borehole properties dialog, you can set the value of wellbore diameter, depth of investigation, and sinusoids drawing reference to ensure that you are using valid wellbore diameter to draw synthetic sinusoids. Now let's take a look at the synthetic sinusoids feature that can be utilized for optimizing operation workflow. Once the image log data is available, you can directly QC your pre-drill analysis with image log data. This red dashed line is the prediction of the top reservoir from the framework. Comparing it with the image log response, we can see the position of the top reservoir is quite a good match with the resistivity log response. Using the synthetic sinusoids feature, I can display the structural properties of the top reservoir and compare it with the image log data. As you can see in the result, the shape is a good match. However, my pre-drill top reservoir prediction was missed by a few meters. Using the guidance of image log data, I can fix the position of top reservoir picks. Using the well pick interpretation tool in DSG, I can adjust the depth of the top reservoir picks to match with the image log. Another thing I can do is add the information on dip angle and dip direction for the picks. Because the shape of the structure is a relatively good match between my synthetic sinusoids and the image log response, I can use the dip angle and dip direction from the synthetic sinusoids and input them here. Now as you can see, I have the high confidence structural framework that both QC'd and matched with my image log data. Combining image log analysis and synthetic sinusoid workflow resulting a powerful during drilling structural adjustment workflow that can lead to optimizing well position on the zone of interest. In this release, we will focus on the 3 new areas that center around the operational geology workflow to support geosteering operations. The first feature is image log interpretation. The feature allows the geoscientist to analyze the dip from the image log and compare it to the pre-drill dip analysis created from synthetic sinusoids. The second new feature is the advanced lookahead. In a nutshell, this feature allows the user to create scenarios of lookahead well trajectory given the relative position of the current drill bit position against the initial well plan and against the reference structure. The third new feature is distance to target analysis. This feature allows the user to quickly create a look-ahead trajectory to intercept a single target within a range of defined drilling parameters. The calculation will analyze the distance needed to intercept the target and the inclination to land the well. The last, we improved HWC layers with adding interpretation locking mechanism and also improve overall usability and user experience of this feature. Image log interpretation refers to borehole image log interpretation. With this feature, the user can draw a sinusoid line that represents the intersection between wellbore and subsurface structure. The image log sinusoid interpretation has data dependency with image log data, meaning user only able to draw a sinusoid line if the image log data is available, and user only able to draw a sinusoid line within the range data coverage of the image log. The dip analysis such as apparent dip, and true dip direction is automatically calculated in the background. The dip analysis is reported via cursor tooltips or well info. The value of interpreting image log during geosteering operation is to make the structural assessment during drilling, so the geosteering engineer can have a better confidence to track the position of the wellbore against the reference structure and help to adjust wellbore placement. The dip analysis along the wellbore can help the subsurface team to update or adjust the reference structure during drilling operation. Once the calculation is triggered, the algorithm in the background calculates the changes in relative stratigraphic position between the initial framework position and the updated position along the look-ahead trajectory. And the engineering parameters of dog leg severity and drop rate are used to snap the active drilling well TD to the updated hybrid well trajectory. Let's see the image log interpretation in DSG 10ep.5.4 in action. First step is to open a well correlation display and ensure the depth mode is on measured depth. Next step is to display the image log on the well correlation view. To start interpreting image log, make sure the image log interpretation type and turn on the interpretation pencil. Notice, when user hover the mouse pointer at the interpretation pencil, it will show the interpretation action for image log interpretation. Click mouse button 1 on the image log to create a sinusoid line. The sinusoid line created will be flat at first. Click and hold mouse button 1 at the sinusoid node, and drag it up or down, to adjust the dip angle of the sinusoid line. Click and hold mouse button 1 at the sinusoid node, and drag it left or right, to adjust the dip direction of the sinusoid line. Hold Shift key and mouse button 1, then drag the sinusoid line up or down, to adjust the sinusoid depth without changing the shape of the sinusoid. Notice, when the sinusoid line created, there will be the header automatically displayed, and show the orientation of the drawing reference of the sinusoid. Now we can see the up right down left up on the header. This means the sinusoids is drawn with the reference of top of the hole. The dip direction of the sinusoid will be calculated according to the sinusoid drawing reference selected when the sinusoid line is created. To avoid any error, make sure the sinusoid drawing reference is set properly before start interpreting sinusoid. When a new sinusoid line created, the previous interpreted sinusoid line become inactive. This means the user only able to edit one sinusoid at one time. To adjust the borehole size and orientation of the sinusoid, click mouse button 3 and go to Borehole Properties. The Borehole Properties dialog allows user to give input value for the diameter of the wellbore, the depth of investigation, and set sinusoid drawing reference for more accurate dip analysis. The adjusted borehole properties parameter only will affect new sinusoid. For the existing sinusoid, the existing borehole properties parameter will persisted. This means the existing sinusoid will not affected by the change of the borehole properties. In this example, we can see that the new sinusoid line will use the updated borehole properties, which is 10 inches wellbore diameter and 2.5 depth of investigation. Where the existing sinusoid will persist the previous borehole properties setting with 8.5 inches wellbore diameter and 1.88 inches depth of investigation. We enable a guidance via cursor tooltips to remind the user of the setting of borehole properties and the sinusoid drawing reference. To activate this feature, click mouse button 3, go to Sinusoids, and click on Current Borehole Properties in Tooltip. So, when the cursor pointer is idle, it will display the information of current borehole properties and sinusoid drawing reference. For the sinusoid drawing reference, when the user changes the drawing reference, for example, from top of hole to north, it will affect the sinusoid drawing globally, regardless the difference in wellbore diameter and depth of investigation. The Advanced Look Ahead is a feature that allows users to quickly plan scenarios ahead of the active drill bit position and target in more complex ways than traditional target line workflows. The Advanced Look Ahead has 3 methods to plan look-ahead wells: back to plan, shift plan to path, and assisted well path update. Advanced Look Ahead is using drilling engineering parameter as input such as dog leg severity and drop rate to ensure the look-ahead plan is drillable. The Advanced Look Ahead trajectory will be drawn as an in-memory well trajectory called hybrid well. The value of having Advanced Look Ahead during drilling operation is to allow the geosteering engineer and subsurface team to collaborate to make the quick look-ahead analysis during drilling, with also include surrounding geology information and relative wellbore position in comparison with the initial plan. Advanced Look Ahead's unique ability to give possible look-ahead scenarios of back to the initial plan, or continue drilling with shifted plan, or with adjusted look-ahead path, will allow geosteering engineer and subsurface team to analyze the best scenario and place the well trajectory at desired position to achieve drilling objectives. A few more details about the Advanced Look Ahead methods. The first method that can be used is called back to plan. This method assumed the scenario when the active drilling well has deviated from the initial plan, and the user wishes to calculate a look-ahead well plan trajectory to get back to the initial plan. The second method that can be used is called shift plan to path. This method assumed the scenario when the active drilling well has deviated from the initial plan, and the user wishes to calculate a look-ahead well plan by copying the ahead trajectory from the initial plan, applying shift, and append to the active drilling trajectory. The third method that can be used is called assisted well path update. This method assuming the scenario when during drilling operation, the reference framework model used for horizontal well correlation analysis is changed, and the user wishes to calculate a look-ahead well plan by updating ahead trajectory from the initial plan according to the change of the reference framework surface. Let me show you in the demo how to use Advanced Look Ahead feature in DSG 10ep.5.4. In DSG session, I have 2 wells. The red well is my actual well and the green well is the well plan. As we can observe, the actual well is deviated from the initial plan. Using the Advanced Look Ahead feature, the geosteering engineer or the subsurface team can analyze the available option to place the well at the desired position. To access Advanced Look Ahead, mouse button 3 at the actual well and select Open Horizontal Well Correlation Workspace, and go to Advanced Look Ahead tab. Now, I have Horizontal Well Correlation Workspace open. As we can see on the well cross-section view, I already have calculated the predicted log curve. The actual gamma ray curve is in blue and predicted gamma ray curve is in yellow. Let's explore the first option, which is back to plan. At this point, I decide to use back to plan for these reasons. First, I consider the reference structure still valid, therefore my initial well plan is still valid. Second, I would like to minimizing the risk. And lastly, to ensure expected optimum contact with reservoir according to the initial model. Let's go to Horizontal Well Correlation Task pane, and go to Advanced Look Ahead tab. Select Method of Back to Plan. Select the reference look ahead well, which is the well plan saved as OpenWorks well. After that, defines the drilling engineering parameters, such as dog leg severity and drop rate. Then click Calculate. Once the calculation initiated, there will be a progress bar on the right bottom side of DSG Windows. When the calculation finished, there will be a pop-up notification, Hybrid Well was successfully calculated. And then, the look-ahead trajectory will be automatically displayed in Section and Map View. In the Map View, we can observe that the actual well trajectory is snapped back to the initial plan and the trajectory is extended to the end of the reference well. In section view, the hybrid well displayed with light blue trajectory. And the actual well trajectory is snapped back to the initial well plan trajectory. The algorithm is using the dogleg severity and drop rate to calculate the snapping point between the actual well and the look-ahead well to ensure the hybrid well trajectory is drillable. The algorithm is also automatically recalculate predicted log along the hybrid well trajectory to give insight of what expected log response on the look-ahead trajectory. Let's try the second option, which is shift plan to path method. At this point, I consider the drilling objectives still can achieved by continue hold the actual well current position and inclination. Then, I would like to calculate the look-ahead trajectory by applying a constant shift of the remaining trajectory of my reference well, and append it to the active well. Let's change the method to shift plan to path, and I will keep use the same parameter input for drilling engineering parameters. Then, click Calculate. Once the calculation is finished, the existing hybrid well will be overwritten. This means user can only have one hybrid well calculated at one time. As we can observe, in the map view, the hybrid well calculated by applying constant shifting in X and Y axis from look-ahead well. In section view, the hybrid well calculated by applying constant shift in and Z axis from the remaining trajectory of look-ahead well. The algorithm in the background will use the drilling engineering parameters of dogleg severity and drop rate to connect and append it back to the TD position of the actual well. Please notice that the predicted log is dynamically recalculated. Now, I will demo the third method available in Advanced Lookahead, which is Assisted Well Path Update. I have a horizontal well correlation workspace open. We can observe that the actual drilling well is on red, and the initial well plan is on green. I also have the reference framework surfaces cross-section in the background. Let's go to the horizontal well correlation task pane, go to the Advanced Lookahead tab, select the method of Assisted Well Path Update. Select the reference well and adjust the drilling parameters. Select the frameworks and reference structure. At this point, I'm going to use the second surface. And then, run the calculation. This is the first iteration of the calculation of the hybrid well. The calculation is needed to calculate the initial relative stratigraphic position of the active well against the reference structure. As we can see in the result, a hybrid well calculated and show the look-ahead trajectory based on the initial active well against the framework position. At this point, the result of Assisted Well Path Update method will be similar with Back to Plan method, as the active well TD is snapped to the initial plan trajectory. For example, there is an updated surface picks interpretation. We observe that the position of surface picks for the second surface is shallower than the framework surface. Therefore, I need to update my framework. I'm incorporating the surface pick into the reference structure in my framework. For the demo purposes, so we can observe the difference in framework update, I assign 1000 meter radius of influence of the picks from the framework source data manager. Then, refresh the framework. After the framework refreshed, we can see that the structure is pulled up to match with the surface picks. The blue line is showed as reference to the previous position of the framework. When the framework is updated, the Advanced Lookahead will notify me of the reference structure has been updated and recommend me to recalculate the hybrid well. Once the calculation is triggered, the algorithm in the background calculates the changes in relative stratigraphic position between the initial framework position and the updated position along the look-ahead trajectory. And the engineering parameters of dogleg severity and drop rate are used to snap the active drilling well TD to the updated hybrid well trajectory. The distance to target analysis is a tool to calculate a look-ahead trajectory based on single target position in the horizontal well correlation workspace. Target position is defined by depth in TDD and inclination. The distance to target analysis is using drilling engineering parameters such as dogleg severity and drop rate to draw the look-ahead trajectory. The value of using distance to target analysis is to allow subsurface team and geosteering engineer to collaborate to make a quick target adjustment during drilling operation, with include geological surrounding available information such as seismic attribute and reservoir model. Allowing user to quickly test the combination of dogleg severity and drop rate to land the well with desired inclination at the target position. Let's see the distance to target analysis feature in action. Right now, I have horizontal well correlation workspace open. To use distance to target analysis, go to Advanced Lookahead and expand the distance to target analysis segment. There are two parameters required to define the target position of the distance to target. The first one is target depth and second one is target inclination. For the drilling engineering parameters, we use the dog leg severity and drop rate value input on trajectory parameters. Now, let me show you how to calculate the distance to target analysis. From the well cross-section, we can see some anomaly and seismic attributes that correspond to good stacking reservoir potential. Currently we are aiming to hit the anomaly at the right edge of the cross-section, which is around 2,830 meter TVD. And I want to land the well at 90-degree inclination. And click Calculate. There will be progress bar on the bottom right corner of DSG. Once the calculation is finished, hybrid well will be drawn on the section view. Once the calculation finished, the distance to target analysis report gives a comprehensive report on how to reach the target. How far the target from the actual TD, and what is the inclination needed to reach the target. User can try multiple scenarios by changing the engineering parameter, such as the dog leg, or change the inclination of the target to find the best combination to land the well. For example, we can change the target depth to 2,827 TVD, and dog leg to 2.75 degree, and it will give us a better landing of the well. Some new improvements we added as part of HWC layers are, first, allowing user to lock the interval of HWC curtain to be edited. Second, we add the feature to fill the HWC curtain interval with the color map based on the predicted log curve value. Third, we adding mechanism for HWC layer to be added and integrated with the framework. We also improved the performance of log curve prediction calculation so it can change dynamically when user edit the HWC curtain. In this demo, I will show the improvements we made for HWC layer. In the DSG session, I have an active horizontal well correlation workspace. I have cross-section display on the upper part of the screen, and I have horizontal correlation view at the bottom part of the screen. I also have gamma ray curve available on the log and a cross-section of the framework in the background. To start interpreting HWC layer, go to Layers tab and create a new interpretation. HWC layer interpretation is integrated directly with dynamic framework to fill. Therefore, I need to choose the framework for my reference structure. Once the framework is selected, and the HWC layer interpretation object is created, in the background, the algorithm creates a framework curtain, represented by solid color lines overlaying the framework cross-section. We added the function to set the zone of influence of HWC layers interpretation to the selected framework. From the map view, we can see a corridor along the well trajectory path displaying the zone of influence of HWC layer to the reference framework. This zone of influence input from the HWC layers will be assigned as input of radius of influence in Framework Source Data Manager. Please note that the zone of influence will affect all the surfaces on the selected framework. The next step is to calculate the predicted curve. For this demo purpose, I'm going to use the current active well as the reference well to calculate prediction log curve. The result of the prediction curve is displayed in green color. The second new feature we added for HWC layers is to fill the interval based on the predicted log curve value. On the interval fill setting, turn on Enable Interval Fill, and the interval will displayed. In this case, it will be filled by the color of gamma ray prediction. This feature can help the user to analyze, validate, and QC the possible continuity of the reservoir against other geological data that can be displayed on DSG section view as background, such as seismic attribute or reservoir model. Let's start horizontal layer interpretation. For the interpretation mode, we add a new locking feature. When the user add the interpretation point, it will be used as an anchor locking point. This means the user will only allowed to edit the layers on the right side of the curtain. This anchor point is critical for HWC layer interpretation, to ensure the structure bounded by anchor locking will not be affected. We also improved the performance of log curve prediction calculation, to dynamically changes when the user modify the curtain interpretation. When the user is finished with HWC layer interpretation, the user can do the last QC by displaying interval fill and comparing it with the other geological data such as seismic, or just by eyeballing the dip change along the wellbore trajectory. Does that make sense? Or there might be some faults causing sudden dip change along the wellbore? You can see there are differences of each HWC layer's curtain against reference frameworks. Because of the framework current status is on dynamic manual, so user need to trigger the refresh of the framework. Let's save the HWC interpretation and refresh the framework. Once the framework is refreshed, the user can run the last QC and check the fitting between HWC layer curtain and the framework position. Thank you very much for your attention. For additional questions and comments, please contact your local Landmark account representation or Landmark support.